Okay, so let's go ahead and get started. I'm Gary Carleton from Intel, and I work on performance analysis tools at Intel. I've been there a number of years. Before that, I was actually here as a student, so this is kind of a coming home experience for me. In any event, I'm going to be talking about sort of a specific problem that has existed for some time in terms of trying to do performance tuning, and that is trying to tune a performance problem that is intermittent and it doesn't really seem to be tied to any specific functionality or problem. So that's essentially the topic for today. I'm not specifically talking about parallel debugging in any particular way, although this functionality is often involved in that. The demonstration I'm going to show is, in fact, a profiling tool that profiles in a multi-threaded, multiprocessor environment. But we're going to be using sort of a separate feature of that today. I think tomorrow afternoon at 1:30, there's another performance session. I think that session and this one are the two performance-oriented sessions. So there's one on performance debugging at 1:30 from a Lawrence Berkeley lab engineer that you can see tomorrow. Okay, so what I'm going to discuss is, first of all, I want to define the problem a little more clearly. What is it that we're actually trying to solve? What are the symptoms of this issue? I'll do a few minutes on the actual tool, the profiling tool, software profiling tool that we'll use to root cause the problem. I'll talk about this specific feature in that tool. We have some APIs and other automatic, automatic time marking, actually, capabilities that allow us to focus in on this issue. And then at the very end, probably most, or at least half of the time, I'm going to show you this technology by invoking a commercial application. And we'll actually do this analysis on the commercial application and see how it works and see if we can identify whether there are random slowdowns occurring in this program, and if there are, what is the cause of it. So that's the goal of what we're doing. I purposely didn't necessarily bring a full hour of material with the idea that you may have questions. So if you have questions, it's certainly fine to ask those. I think if they're quick questions, I'll just repeat them. Otherwise, we have a microphone in the back that will be moving around if it's more of an essay question, I guess. Okay, so let's talk about the problem definition. This really relates to a particular sort of customer segment that we have for our performance analysis tool. Over the years, this tool's been around for, I guess, about 18 years now. So over the years, I had a number of developers mention that while the performance tool that we have is very useful, it tends to look at performance as an overall aggregate of what happened during the entire run of the program. This particular segment of the market wanted to look at more like time slices, not slices maybe, time segments of the overall run, and to be able to look at performance within the perspective of this particular run. The applications I'm talking about are actually video games. I used to visit video game companies a lot, and they would say that their issue with performance is not how fast does the overall game run in an aggregate way. They need to be able to do performance tuning within each video frame time. They have to get as much done before the next video still goes up on the screen so that they can simulate motion that's smooth and they can have a game that feels like a realistic experience. So they would have this issue of within one frame time trying to do a little bit of physics in terms of things moving around on the screen, shading, lighting, maybe some sound, maybe a little video. There's many different kinds of things that they need to get done within this short window, but it's a repeating window. So they had always asked us for this capability of looking at things with respect to sort of frames within the overall run. So we thought about that. About 5 years ago, we did a complete rewrite of this tool, and we wanted to include some type of functionality like this because it seemed like a good idea to us, but it was kind of a whole new model, so we didn't want to do it in a minor release. So we thought about this, and this certainly makes sense to try to look at performance analysis in terms of video frame times. But as we thought about this more, we thought, well, many different types of applications have this concept of a repeating high-level functionality. So the ones that immediately came to mind were databases, where a company that has some type of query capability is trying to read the query in from the user, do the lookups into the database as fast as possible, and produce results quickly. So there's this idea of every query you want it to be fast. So you want to sort of tune the query time. Computation, there are many examples where there's a repeating functionality that keeps going and going. Now, perhaps as we've all seen in our own experience, oftentimes, you're running some program and it seems to kind of slow down all of a sudden, whether it's an operating system or an application or an internet browser. There's often this occurrence of something just kind of slowing down for a little while, and you don't really know why. There's no case for this to occur. In the case of myself or other users, it's just kind of an inconvenience. But if your company depends on giving results quickly, this is a very serious issue. So we wanted to try to address this idea of every once in a while something slows down. How can you focus on those events where the slowdown occurs and do something about them? Okay, so that's kind of the problem that we're trying to solve. Again, not looking at how fast a program runs overall, but trying to tune individual instances of a functionality, of a recurring functionality. So let me spend a few minutes talking about the tool that we have that does this. Now this tool, the VTune Amplifier XE, is a general software performance profiler. It doesn't just address this type of frame analysis or epic analysis. So I'd like to give you an overview of the tool, talk to you a little bit how it works so that you can understand what's going on underneath the covers here, so to speak. And then we'll go into the detail of this particular problem. I think one thing I always like to ask at these kinds of talks, has anybody heard of the VTune amplifier? Generally, I get more hands than that. Okay. Yeah, okay, so let me rephrase that. I always say VTune amplifier because that's the legally blessed term in terms of our trademarks, I suppose. Maybe I should not be quite so specific. So, anybody heard of VTune? Okay, we got a few more hands. Anybody used it? Okay. Okay. So we've got a range of answers here. Okay, so let me describe what it is a little bit. The goal of this is a performance analysis tool. We're really trying to identify where there are software performance hotspots, either in your program or elsewhere in the system. The main philosophy behind this tool is low overhead at runtime, or low intrusion. So with this tool, we want to gather performance data, but we want to do it in as natural and normal and unaffected an environment as possible while the data is being gathered. I'll talk about the technology that we use in a minute. But that's really the goal. Let the program run, let it run as it normally does, and we'll just sit in the background, gather performance data, and then ultimately look at the results later. So this screenshot is a look at the first meaningful set of results that comes up on the screen after the data's been gathered. We'll take a closer look at that. We have a timeline view that shows activity in threads as the program ran. We're compatible with a number of different compilers. Essentially, The compiler dependence here is we support either Windows or Linux, the two operating systems, Windows or Linux, and we'll support any compiler that is a native compiler that produces assembly language or machine code and produces a symbol format that's any kind of industry standard. With this tool, there's really no dependence on parsing source code, or is it Fortran or C++ or just C. That's not really the issue. We also support a few managed languages, C# in the .NET environment, Java in other environments. And as I mentioned, the support is on Windows and Linux. Okay, so yes. Is it free? It's an interesting question because the answer is yes and no. I guess we can start with the free versions. There's an evaluation version, so you can just go onto the web and download it. I'm not sure what the term is. It's either 30 or 90 days. There's a commercial version, which is the normal one that companies buy, and there's different kinds of licenses and pricing based on volume. But there also happens to be an academic license that I actually don't know much about because I tend to work with bigger companies, not so much university. So that's the best answer I have. Okay, so sampling technology. The way VTune actually gathers performance data, there are a number of tools that will instrument the program in some way. Either you have to run a special compilation on it that produces profiling hooks. You may have to instrument the binary at runtime. There are profilers that do that. What we do, again, is try to not require anything special in the system and to have software that's your normal build. So the way VTune gathers software performance data is by simply firing off periodic hardware interrupts and saving away the execution context that's seen at the time of the interrupt acknowledge. So we're essentially not looking at everything that's going on in the system. We don't look at every instruction that passes through all of the different cores. We're simply occasionally taking a look at what's going on and then drawing conclusions based on that set of samples that is collected. So with every interrupt, we save away the execution context. There's actually a set of ring buffers that we use. When one fills up, we start to spill it, and we use a second one. But the main point here is that there's no profile build. We don't expect you to do any special build of the application. Just use your normally fully optimized build with symbols enabled, which gives us the ability to show you annotated source code with performance information. Okay, so this is a look so that you can understand the results that we're going to see when we run this application. This is a look at the GUI that represents the first really meaningful set of performance data that you see after the performance information has been analyzed. So we have here in kind of a spreadsheet form a sorted list of the functions in the program, sorted by CPU time. Also with the calling sequences that called the function listed, with each one of those calling sequences noted as to how much CPU time was produced. So here we see grid intersect being called by a separate function and being called recursively at the same time. Well, not at the same time, in the same program. We also have the thread timeline, which essentially allows you to kind of look, get a high-level visual view of what was happening to your threads as the program was running. Did they tend to be busy? Did they start right away? Did they end prematurely? Things like this. You can just kind of get a visual look. If you double-click on a function name, you then get the source view, where VTune picks up the source code and then annotates each executable statement with the amount of CPU time consumed by that one statement. So this is kind of the normal endpoint for VTune analysis. You want to be able to look at your source code and know where the performance data is where the performance, the CPU performance, is really going. And this also represents probably the most common mode for the VTune analyzer. Just run the application, look at the list of hotspot functions afterwards, and then drill down into the specific source to see where it is that you need to think about changing the algorithm or recompiling more aggressively or something like that to get the program to run faster. It's a normal profiling mode of VTune. Okay, so that's a quick overview, a really quick overview of the tool itself. Now let's talk about this idea of trying to look at performance in terms of specific time segments as the program ran. Our term for this is frame analysis. So I'll talk about two things. We have an API, if you want to use it, to identify those points in time where the application has started or ended a specific functionality that you're interested in. And also talk about how to look at the results of the profiled data. Okay, so we added this capability of identifying frames within the program where the user can add APIs into the program to tell VTune, I'm starting an important functionality right now. Sometime later, it just finished. And then sometime later than that, I've started it again, it's just finished again. So the idea is to inform VTune at runtime with these APIs as to where the points in time are in terms of the starting of this special functionality that you have and the ending of it. So that's one mode, a user-defined mode. And the APIs we show here, basically, you just call VTune at the time that the special functionality, user functionality starts, and then you make a second call later when it ends. You also define the particular frame. You can have multiple of these frames in your program. So there's an initial creation of the frame. But the idea, again, is to be able to look at the performance data subsequently and see where these boundaries in time are in terms of your particular functionality. The two ways that VTune has for collecting this data are, first of all, the APIs that I just described. So any program can put these APIs in. But also, sort of based on this feedback that we got from the game developers, you can request VTune to automatically capture the rendering of DirectX frames to the video buffer. So the two ways of gathering the data are, if it's video information you're interested in, you can tell VTune, just tap into Microsoft's DirectX and see when the frames started and end. Or you can do your own customized version of this with the APIs. Okay, this is where I've been trying to get to. So, like I say, these game developers had been telling me this for years. So when we finally got to the point of rewriting VTune, maybe more than that, probably 5, 6, 7 years ago, we wanted to put in this idea of frame analysis, just like the game developers suggested, but we wanted to make it extendable to other types of applications. So before we implemented it, we talked to a few customers. I went down to a web search company that you have heard of down in Silicon Valley, and I said, we've got this idea. Your biggest problem is when a user goes to your website and enters a web search query, you want those results to come back as fast as possible. You need to tune that response time. We have a functionality where you can isolate each specific query that comes in, and you can do tuning in relation to these queries and essentially be able to speed up the average response time for your customer entering these web searches. And it still stings a little bit. The reaction I got was, engineering manager there said, you don't understand the problem that we have. We think our average response time is fine. We think we're just as fast or faster as that next company, Up 101. But the problem that we have is every once in a while, it takes 10 times longer for that query answer to come back. We cannot have our users sitting there at our web browser and waiting a full second or 5 seconds for the answer to come back. We don't need to tune the average time. We need to tune these outlying transactions that take much longer. We have no idea what's happening. We don't know a tool that can look at just those randomly occurring frames or randomly occurring queries. And we need to know what's different about what's executing when it goes slowly as when it runs fast. So we left and we thought about it for a while. We came up with this idea of slow frames. So what we added was a new sort of mode of displaying the performance data where we include a frame type. So all the frames that were gathered during runtime are categorized into 3 different types. Frames that were fast enough, good frames, unacceptably slow frames, and frames that were fast. So every frame that comes in gets placed into one of those categories. The idea is that all the slow frames now represent one subset of the database. We can look at all the slow times as a single unit of performance and understand what's going on there. In particular, we can expand this slow frame node and then see what's going on in the slow frames. And similarly, we can expand the good frames and see what's different. The idea here is to figure out why the slow frames are slow and to actually look at what's going on when the slow frames are executing. So this is a way of isolating, essentially, those points in time, or not points. This is a way of isolating those portions of the overall run that were involved in frames that were unacceptably slow. We can then look at the difference between those good frames and those slow frames. Also down at the bottom, we show some more information on the timeline. Here's the instantaneous frame rate. You can just hover the mouse and you'll get information on what the frame rate was at that time. Also, these blue depictions indicate the start and end times of frames. So you can kind of get a visual look at how frames are going. And you can, again, hover the mouse pointer anywhere and you'll get information on that particular frame that existed there. So this is the idea. I wanted to set the stage here. We run an application. We tell VTune either through DirectX Video APIs or through the VTune APIs as to what the frame instances are that we're looking at. And then VTune, in a post-mortem analysis mode, will pull apart the ones that are slower and hopefully show us what's going on with that. Okay, the next step is the demonstration. So do we have questions? Come on, think of some questions. We're gonna end early if you don't think of questions.
I have a question, but it's a little bit to the side.
Okay, well, give it a try. Do you want?
Well, I want to tie it back into the previous speaker. I believe your compiler, the Intel compiler, supports OpenMP.
Right.
Do you have support built for OpenMP?
We have some support for OpenMP. It's not as direct as you might say, but if you have OpenMP pragmas in your source, VTune will still understand that there are threads involved in the for loops typically. VTune also, actually that's a pretty good question. When I say that we'll show you the amount of CPU time on any particular executable statement, that's an aggregate of all threads and all CPU cores in the system. So in an OpenMP sense, you could have multiple threads operating on a statement, and that executable code can run on a number of different cores at the same time. What you see here is all of that aggregated into one number. You can ask to split it out by core or by thread, but the default is show me everything at once. Say again?
You do have the capability of focusing in on the core.
Yes, right.
It's different ways of slicing.
Actually, just to finish that off, I mentioned this sort of spreadsheet mode up here where in this case, instead of looking at functions as the highest level, we're looking at frames. There's a set of modes here. There's like probably 30 different modes, and maybe 5 of them include breaking it out by core, depending on what order you want the hierarchy of the display to be.
And that includes logical cores as well?
Right. Anything that has a sort of a core context, we assume is a core. So hyperthreading cores are included. Yes?
Is there any way to inspect the cache performance? Because cache can be a problem.
Yes, absolutely. I can't even begin to describe how many things I'm leaving out here because we're only talking about this one functionality. But yeah, actually, that's easiest to show in the demo. But just as a summary, yes. Kind of the original purpose of VTune was to be able to look at cache misses and to identify how many cache misses there were, at which level cache they were occurring, and also where in the source code those cache misses are being generated. So we do all that today. With today's VTune, it's more automatic. You don't have to be a total architecture expert to figure out, how do I express to the GUI exactly which type of cache miss metric am I looking at? There's a little more high-level information, but cache misses are a key part of this. For this simple example, we're just looking at CPU time, but this could apply to caches also. Other things, the other performance metrics that we look at, basically supported by the processor, would be branch mispredictions, bandwidth capabilities, misaligned data accesses. There are actually hundreds of these little events that we can look at. Yes?
So follow-on, how about GPUs? Can you handle those?
Not as I stand here in a public forum today. I guess that's not totally true. Depends on how you define GPU, but you may know we have a relatively new processor called the Xeon Phi coprocessor. So we do support that in the same way. This is the massively parallel, sort of minimum 60 cores per chip kind of a thing that works normally as a sort of a secondary processor to Intel Xeon processors. So VTune can collect similar types of information there. Pretty much well beyond what I'm going to talk about today. Well, these are good questions. Anything else? I'm kind of delaying because this demo, the VTune part of the demo is fine, but it requires me to run the application correctly, which is a little bit of a challenge. But I guess if we don't have any questions, let's go ahead and do it. Okay, so I'll start the GUI version of VTune. This happens to be on Windows because the application I'm going to run is a fairly well-known Windows application. So we have a command line version of VTune also. You don't have to use the GUI, but it's a little easier, I think, conceptually easier in this kind of presentation to understand what's going on with the GUI. Let me talk about configuration for a minute and perhaps address some of the questions. Over here, so I clicked on this sort of DVD play button that is essentially the configuration screen. This lets me set up a test for what we're going to do. For this particular run, I'm just going to select normal hotspots. But we have the ability to select a number of different types of performance data to be gathered. Memory access would be the one that includes the common cache miss things. General exploration is kind of cool. That one is where essentially the user tells VTune, I don't know why this program is running more slowly. You just gather a bunch of different kinds of performance data, and then let me know afterwards with the GUI whether you think there's a performance problem with caches or what. So general exploration is just kind of what it says. But you can focus in on memory accesses if you want. Locks and waits is kind of an interesting one, where VTune is essentially not so much looking at CPU performance, but it's identifying reasons that threads block. It's a little bit of a higher level kind of model of looking at performance. It's not so much how fast is the CPU executing instructions and that type of thing. It's more when threads block, what's causing the block, and VTune will ultimately show a sorted list of synchronization objects or APIs or I/O operations that are causing threads to block, sorted by the individual ones that are causing the most blockage to occur. So that's another new technology that we added, but that's not why we're here today. So we're going to select hotspots. I'm going to indicate that we're going to analyze, that we want to analyze DirectX frames. So VTune will intercept the APIs that hand a DirectX video frame to the buffer, video buffer. Project's properties is where we would go to configure more details about what's going on. I've configured in there the name of the application that we're going to run, and I've indicated that we want the application to be started by VTune. It's not one that's already running. We could certainly profile that, but in this case, that's not what we're doing. So let's just go ahead and start the application. So we'll start up the application. VTune will begin gathering performance data immediately, and we'll see how this goes. So I'll click Start. And the application that we're going to run is Microsoft's Flight Simulator. We're going to try to land an airplane at San Francisco International Airport during a rainstorm with turbulence and limited visibility.
Is that on autopilot?
No, it's not. I hadn't thought of that. So I wanted to add the turbulence and weather in to give the software enough stuff to do. But as it turns out, it makes it much more difficult to actually use. So I practiced this a number of times right out in the lobby out there, and I was not successful each time. Okay, so here we go. It's paused right now. The airport is up there, but we're far enough away we can't see it. I guess for your information, this instrument is the one that indicates whether we're aimed correctly at the runway and what our relative height is. We'd like that to normally have both of those centered. I started it up not quite centered, so here we go. Okay. Looks like, wow, we got a lot of bad stuff going on. I pretty much just have to fly. I can't really talk about what I'm doing. You can see that those needles are not. Oh, there we go. Okay, so now the airport's in view. Okay, so I'm going to drop the throttle a little bit. I want to descend and not go too fast. I say again, we want to descend. Okay. I'll add in one notch of flaps to get this plane slowed up a little bit. Those of you that can see the airspeed indicator, we sort of want to normally be at 60 knots. I'm coming in a little fast. Also, you can see the runway there. Those lights to the left of the runway are the precision approach path indicators. When they're all white, that means you're too high. But given our situation, I think too high is probably okay. It's a hugely long runway, so we don't have to put it down right on the numbers. Okay, so I'll add full flaps now. See if we can get this thing landed. Oh. Yeah. Okay, power to idle while we touch down. Yeah. Okay, looks like we landed safely at least. Maybe it wasn't. Thank you. It wasn't pretty, but we're alive.
That's water on the runway?
That's water on the runway. Okay, so now we'll quit. That's the hardest part of the presentation. The rest of this is trivially easy. I've been worried about this for a week, at least a week. Okay, so the game finished. The application finished. VTune's now analyzing the data. It had all those samples of execution context. It's now mapping them into each different dynamic library that was loaded, attributing samples to each one of those, and it'll show us kind of a summary of information first. Okay, so it's showing us function names that consume the most time. And by the way, this is the game right out of the box. I don't have source code. I don't have symbols. The only symbols we have are the entry points into the different DLLs of the application. So let's look in more detail at what's going on. And here we have that screen I was talking about. We're requesting to look at frame information, and we're seeing that for a portion of the run, there were no DirectX frames being generated. So this is the initialization of the program. I think maybe there are portions where it's just loading scenery in, that it's not really generating DirectX frames. But we do have the major part of the application, DirectX frames were being generated. Down here, as I mentioned before, we can see frames. We can just put the pointer anywhere and see what frames were in that narrow little point of time. Down at the bottom, we have the frame rates, and in fact, we see there's some initialization where there's no video going on. A little bit, and then not much else, and then the game really starts up. So let's expand this DirectX node and see what happens. Good. This is the kind of data I'd hope to see. Okay, so DirectX is broken up into 3 frame rates. We have the fast video frames, acceptable video frames, and the slow frames. So out of the 157 seconds that we were rendering to the screen, 153 of those were just as fast as we wanted. But there's 4 seconds here worth of the video frame rate slowing down. This is what we don't want to see. So what we can do is analyze this in a little more detail. We can expand the slow frames. And we see some functions here. Probably makes sense to look at the top function. So this function ord23 consumed 1.2 seconds out of the total 4 seconds that we had slow frames. So that's what, maybe between 25 and 30% of the total slow frame time is this one function. If we look at the good frames, so this is ord23. We look at the good frames, the acceptable frames. We see ord23 down here at 5 seconds out of 153. So it's like 3%. So normally this function is 3% of the CPU time. But when we have slow video frames, it shoots up to 25 to 30%. There's something about the executing of this function that is slowing frame time down. Well, if we look in a little more detail, we see the different module names, the different dynamic libraries that we're executing. We see that ord23 is in the terrain DLL. So what I believe what we can conclude from this is that as the plane's flying along, every once in a while, we have to spend some cycles recalculating the surrounding terrain so that the game can both depict it on the screen and check for crashes, check for you flying into the terrain. So it appears as though it's the occasional executing of the terrain system that causes the frame rate to slow. So this is kind of I wouldn't say it's a simple example, but this is one example of this idea of isolating all the slow frames, the slow execution times in your repeating functionality, and then looking at what's different between the slow frames and the fast frames. Questions on this? Okay, a couple of things I wanted to show. So in terms of cores, someone asked, can you look at specific CPU cores? So that's it's in here somewhere. I'm not finding it immediately. But there is the ability to look at specific CPU cores in that manner. Also, we have kind of an overall summary, as I mentioned, of what's going on. A little more detail on the frames in the frame display. We can zoom in and take a look and see that every once in a while we get a frame drop going on also. Okay, so that's pretty much it. Again, I expected more questions. Any questions on anything VTune related? Did you have a question? Sure.
Are there any competitors to this performance analysis tool? I've heard some small startups like New Relic, but they don't seem to be as precise.
Yeah, there are a number of performance tools on both Windows and Linux. You can probably start with Windows Visual Studio. The development environment has a profiler that has some similar functionalities. I don't personally know of one that has this kind of frame focus kind of thing, except in certain game development systems, there are video frame profilers that focus on this. But that's, you're doing a video game in this one specific hardware environment. Other than that, on Linux, there are also many profiling tools, but I don't think there's one that does this. Perf, OProfile, probably the two most common that we see on Linux. Yes?
Is there anything similar for macOS?
For macOS, very good question. So you may be familiar with about almost the same time frame, maybe 6 or 8 years ago, Apple started using Intel processors in their laptops. At that time, or actually, let's just say at that time, we started having meetings with Apple as to what we wanted to do about performance analysis. And they had at that time this tool called Shark that you may be familiar with. So we talked to the Shark group. I was in a couple of meetings with them myself, and we ultimately decided that Shark was a great tool, and we just didn't, at Intel, we didn't need to spend the effort to move VTune over when there already was a good solution that could look at cache misses, could look at CPU time, gives pretty interesting advice, actually, when it can see that there's a particular kind of thing wrong. Good graphs. So we sort of decided not to do it for Mac OS. Now, as I understand, they've moved on to a tool they call Instrument is the version now. I'm not sure Shark is still around, but that was our feeling, was that, Apple's got it under control. We didn't need to move over there. Yes?
Can you analyze clusters with this? This is a one system example. Is it possible to do clusters?
Yes. Interesting question. I was at some national labs just a month ago, and I got that daily. The answer is not really. VTune only looks at one system at a time. And while you can certainly gather performance information on one system and then another and then another, we have the ability to compare two different sets of results. But that's it. You can't. So the answer is really no, I would say. Although we have a little bit of MPI functionality, if that's the cluster environment you're thinking about, where you can run VTune pretty much tied to a specific rank in an MPI area. But we really don't have, with this, we don't have the bigger picture. There was a tool from Germany 10 years ago called Vampire, you may have heard of. We ended up purchasing their technology. So we have a set of tools that we call the Trace, Analyzer, and Collector that are meant for MPI clusters. So you can do some of that. It doesn't have this low-level frame functionality, but there is that capability. More questions? I guess I didn't do a good job of repeating the question. But okay, well, I guess that's it. Appreciate your time, and I enjoyed coming back to the campus.